It's time to start the last session of this year's summer school. It has been a great week, I think, and thank you all for attending and contributing. And this is the intensive schedule we have had. So in the coming 30 minutes, I would sort of want to wrap up and provide a couple of complementary perspectives. And so this was the first slide I showed to you, and this also shows sort of the complexity of CPS. Many different perspectives. Here's another view which is a little bit structured by trying to capture the same. So we have at least touched upon a number of application domains involving a number of properties, a number of technologies, and so on. And as we heard from a number of other talks, at least to some extent, we are fitting these CPS in our societies. So these are not just technological systems, they will change behaviors. Behaviors of people will impact the systems, and we need to get legislation and ethics and other things in place. We can reason about the properties of these systems. We can talk about different types of CPS. Many systems will, of course, have humans in the loop somehow as developers, users, maintainers. Technology, all the different types of technologies. We have touched upon a number of recipes, processes, and standards. And then here we have also talked about the complexity. Here we have touched upon a number of tools to work with cyber-physical systems. But as you have seen, these tools are really disciplinary. They will help you to model state machines or continuous time or safety cases. They help you with a certain aspect of these systems. And Valid started talking about modeling and the important role of modeling, not the least in communication and increasing awareness. Co-design is something I tried to emphasize really strongly here. So we are talking about cyber, computer, feedback systems, and electronic, mechanical, and other types of physical systems. So co-design in the broad sense involves all of that. And I'll come back to that. We talked about key trustworthiness properties. We talked about this aspect of first principles modeling, model-based versus black box, machine learning, deep learning, and in particular we had Hans-Petter Schöner talking about V&V. Okay, so this is a complex landscape. So how do we navigate cyber-physical systems? I wanted to give you a couple of snapshots. So first of all, we could just look at the disciplines. And I think in a nutshell, this is a key aspect of CPS, that we have had robotics people work on one end of the campus, and we have safety people working on the other end, security people, and now they really need to come together. And as we heard from Herman and from Pernilla and others, we really strongly need to involve the non-technical aspects as well. So how do we navigate? UC Berkeley had a strong role in developing the concept of CPS. If you Google a concept map, you will have one view of how you navigate CPS. And this actually continues down here. And I don't know how readable, sort of readable. But as you can see, let's see if you can see. Maybe it's not super clear here, but a main emphasis in their take on CPS, led by Edward Lee and others there, is really on modeling cyber-physical systems and having different types of models, in particular behavior models, and how you compose them and reason about system-level behavior. So you have very strong emphasis on the modeling aspect. So this is one view of CPS. If you go to NIST, the National Standardization Institute in the US, And if you Google CPS framework, you will find their CPS framework that they developed through a number of workshops with experts. How many of you are familiar with the concept of an architecture framework? A so-called AFFU, yeah. So architecture frameworks have been adopted in systems engineering, and essentially what they do, they are used to help in dealing with complex systems. So they would define what are the key views or models or perspectives to a complex system. So you will find architecture frameworks for enterprise computer-based systems, for example. Different types of such. But here's the framework they developed for CPS. And as you can see, timing is one key aspect they are putting forward here. So here are like key perspectives that the experts that met in those workshops identified. The life cycle, for example. You see trustworthiness here. And then they have also emphasized so the life cycle is here, but they also have sort of 3 life cycle related perspectives here. The actual design, requirements, for example, describing the context, the operations that are expected, the actual design, and how you do the assurance. So the safety case model would end up here. So I wanted you to at least see these. They don't give the full answer, but if you struggle to structure what is a CPS, all the aspects, at least you have some references here. So in these things, we talk about different views or viewpoints. And let me see. Okay, this is the one I had first. So here's just one example. We can talk about different views of a complex system. And example views of a CPS is that you have, let's say, a mechanical engineer that would be looking at the physical system. And doing a juggling robot would look at, what kind of actuators, what kind of linkage. Should it be a humanoid? Should it be industrial robot type? This is one viewpoint. And in that viewpoint, typically you have certain concerns. You often have cost, right? You have performance. You might have dependability related concerns. And then you have the control guys, you have the software guys, and so on. There are other ways to cut this perspective. Life cycle is another way. So we could have a maintainer of a system, for example. That would be an example of another view or viewpoint. And as you can see here, just to give you one example, so the control engineers, they would be looking typically at typically they look at performance of a closed loop control system, and they look at robustness, and that results in an algorithm. And they take certain things into account here. There are certain things they include in their models. Typically, they have very little or very, very, very simple rudimentary abstractions of communication delays or something like that. Although that is being more and more recognized now. So we have systems where we have different stakeholders, they have different views, they have different things they are interested in. And normally they are not always aware of the other viewpoints or of the concerns of the other viewpoints. And perhaps they are not aware, maybe they are aware, but they are perhaps not aware of where there are tensions between these viewpoints. So just to summarize here, so we have design and co-design. And for example, if we take the example here of developing an automated car, so there is, let's say we have a designer here who wants a really nice shapes of the car, looks and feel. And then we have a sensor engineer here that wants, dedicated space and free side for the sensors. And now if you shape the size and the features for look and feels, that would have an impact on how you place the sensors. and the materials that you put in there will impact the dynamics, which will impact the controls and so on. So there are lots of coupled design problems here. We have seen many toolkits here. We have talked about emergence, and many of the properties we talked about, such as safety, are system level properties. So a piece of software, we cannot, in the system safety sense, we cannot really say if that piece of software is safe, because that will depend on how we use it in a particular context. So there might be some bugs in that software. They may be relevant in a particular domain, they may not be relevant in other domains. The interplay between software and hardware will play a role. So these properties, that's why, for example, you can sort of pre-certify components, but the final certification always has to be done for a complete system. I will come back to architectures in a minute, and then we have more and more complexity, and we need help from Herman and others. We need all the means we can to fight the complexity. So let's see, I wanted to give you one example here of different viewpoints, and this is just a snapshot. So at KTH we developed something we call dependency models, and this is kind of abstract, but let's say we're developing a juggling robot or another type of robot, and then we have design decisions that we make. We have to pick sensors, for example. We have to pick the types of arms and the lengths of the arms, so-called synthesis dependencies or synthesis decisions. And when we have made certain decisions, if you remember the dynamics talks, then we can compute things like dynamics, inertia of mechanical systems. Some things follow directly based on decisions that we have made. So the idea here that you can describe this for a discipline, this would be mechanical engineering. We make choices and we get sort of emerging properties. And then we have control engineering and we make other decisions. We want to decide on, for example, at the top level, we want some accuracy of the controller. We have to decide on the controller strategy. And the interesting thing is really here is the intersection, how these different viewpoints interact. And I just wanted to show you one example we did on the robot design, where you have the mechanical viewpoint, the control viewpoint, and the, let's say, the controller embedded systems viewpoint here. So here, the software electronics designers are making choices, control designers are making choices, and then the interesting thing is what happens in between here. So for example, as Herman mentioned, we need to choose sampling periods at some point in time. And they are typically chosen by the systems engineers or the control engineers. So there's a choice made here on the sampling period. The sampling period, as you know, will emerge in the software in terms of constants in our control algorithms. It will emerge as a constant using setting up a timer interrupt. So we will have a dependency in here. At this end, we have things like execution time that is emerging. Execution time contributes to the overall end-to-end delays we have. So these are just examples and illustrating the dependencies between the viewpoints. Okay, I mentioned architecture. And architecture is a term that's used very, very differently. And if you want to be ISO compliant, if you want, you don't have to be, then you should have a look at that standard, which defines the concepts of architecture, views and viewpoints. And it talks about architecture as the sort of the fundamental properties of a system in terms of how we set up our overall organization. For example, the hierarchies, the connections, the scheduling strategies, the control strategies. It's kind of an abstract concept. Another view talks about function or behavior on the one hand, and structure and components on the other hand, and how there is a mapping between them. So we can think of behavior. We want to accomplish an abstract behavior, top-down, or we can think about, I have some interesting components. What behavior can I achieve? Okay, so let's see. I wanted to say something here. What did I want to say? Yeah. So this standard also then defines the concept of views and viewpoints. And actually, the terminology they use there is not to talk about. They talk about architecture as an abstract thing, and they wouldn't say hardware architecture or software architecture. They would say the software view of the system architecture, the hardware view of the system architecture. That's the proposal in this terminology. Okay, so to wrap that up, when we design the CPS, the juggling robot, the automated car, in general we have a very large design space because we have the physical and the cyber domains. And on the one hand, we have to think about what functions are really important to put there, so to try to avoid the featureitis. But since we are never designing from scratch, we are always reusing more or less novel, more or less revolutionary, more or less evolutionary, legacy-based. So basically, we will always have more functions than we want, but we should do what we can to avoid the featureitis. And then I mentioned in my first lecture the different types of complexity. So in the software domain, the state space, the connectivity, the resource sharing through the computing systems, and in the physical systems, the different types of physical phenomena and how they interact. Yes?
Question.
Yeah.
So, as you know, I kind of belong to the community who tries to manage its features, and according to them, they're inherently good, I guess. So I'm wondering, is featureitis an established term in some other community, or is it
I don't know how it emerged, but I guess some people, as you saw the Spanish group survey, they showed that in software systems, you tend to use a very small part of your software. And I think the problem is especially for software, because it's so seemingly easy to add new features, but each feature has a cost, a hidden cost. So, I mean, yes, you need to do your feature analysis, but interacting with the stakeholders and understanding what is really core and what are essential features and what features will not be used. So, useful features, featureitis. Yeah, thank you. Okay, a very important takeaway for CPS or any complex system is that the environment is extremely important. And with environment, I mean the near environment, the bigger environment. The CPS acts in an environment. It's not isolated. And it's designed to fit in an environment. If you don't understand your environment and the stakeholders, this is where you need to start. And you need to look at the stakeholders. And this is a common term for the system of interest. You're building a system, your system of interest, in a particular environment. You have to understand the usage, and that means both the intended usage, the non-intended usage, and how it might be misused. And of course then also the what might go wrong, both in terms of safety and security. And basically I already mentioned this, but the stakeholders is sort of whatever system you're dealing with, whether you have a new role at university or you're building a house or a CPS, you need to understand the stakeholders and their interests. And I think we have had a nice doses of human CPS. At Berkeley, there is an interesting center called Human Compatible AI, led by Stuart Russell. So there are AI centers and a center for human compatible AI. We want to have human compatible CPS, I'm sure. Yes, and then collaboration and communication, we have talked about it many times, and it has many facets. So there is the communication inside an organization, there is the communication and collaboration with external stakeholders, and for an operational CPS, it also needs communication and collaboration. Okay, so basically that leads us back to CPS. And I hope I have convinced you that there are different types of CPS, and the definitions only help us so far. We need to clarify our interest in what type of CPS we are working with. And CPS are not new, but increasingly integrated, also bridging different domains, increasingly capable, increasingly acting in uncertain open systems. They are also increasingly live, meaning that they are connected, they can become upgraded, they can become, the parts may become reused for sustainability, and increasingly society scale. So smart cities, smart transportation, we will increasingly be relying on, already today, as you know, in the security point of view, many systems that did not used to be connected are connected. So our energy systems, our water systems can already today be compromised. And this is just the beginning. Tomorrow, most of these systems will be interconnected. So we want these systems to be trustworthy. And moreover, they are becoming data-driven because they are connecting. Much more data is available. And they are more and more also becoming provided in terms of services. And the final point here is that CPS are also important. I think some group mentioned sustainability here. Sustainability has different dimensions, and one is environmental, there's economical and social. But for all, CPS is really has the potential to help us to deal with sustainability. But we also have to think sustainability when we develop these systems. We cannot just deploy electronics and batteries everywhere. They have to be traced, they have to be reusable, recyclable, and so on. And here there is a very interesting role for example, architecting these systems to be part of a so-called circular economy. There's a big room for contributions there. Okay, so we talked about open systems, and there is this interesting cone of uncertainty known from engineering design. And basically, we all know that when we start to build a system, there's many things that we don't know. There's a lot of uncertainty. And as we work, we gain knowledge and we make more choices, we learn more. And for classical systems, we have reduced this a lot, we have gained a lot. But essentially, with open systems means that this gap is becoming larger. And that has to do with the inherent complexity. So we have an increasing cone of uncertainty. And that has to do with the openness, it has to do with the environments, it has to do with the fact that the use of the system changes behavior, so the world is not static. And as we mentioned before, this means that it becomes even more important to build systems that are, as Sagar explained yesterday, security, there is a lot of knowledge out there, you should use it, but you can never be foolproof. Systems will be hacked and they will break down. And because you have this increasing degree cone of uncertainty, you need to build robustness and resilience into the systems. Okay, and then I usually make the analogy with gold rushes. So there's a lot of market-driven developments. It's very noticeable in the automated driving. Billions are flowing all around the place. It's really a modern gold rush. Someone told me at the European Commission that there is no more than 1,000 IoT, Internet of Things platforms. And why? Well, I think that's another gold rush. So the people think that we can make a lot of money. We will provide the platform. And of course, in AI, we see similar things. And what this means is really that there are lots of opportunities. There is not so much collaborations. Many of these things have not converged. They haven't been standardized yet. And that means that the tools, the platforms, the engineering methods are fluid. We are doing a survey on tools to do modeling and simulation for automated vehicles. And we have a nice overview picture. And essentially, whenever we meet a new company or organization, they are using a new tool. Or a new set of tools. And many companies will say, well, we have the silver bullet tool. But yeah, it's just an indication that the market hasn't stabilized. Yes, and then I think in particular then trustworthiness needs more of energy because the gold rush, the market is pulling, so we need to hold back and steer the directions in the direction of trust. Okay, so many people call this a technological revolution. In Germany, they call it the fourth industrial revolution related to Industry 4.0, which is a domain incarnation of CPS. And, well, I think we touched upon some of these, but looking into history, it's interesting to relate back. For example, if you take any of these, you will see similar patterns. So in the old days, transportation was through horses. And then steam engines appeared. And they were exploding, they had poor performance, and they were not worried. Or maybe a little worried. And then after a while, performance was on the par. And then what did they do? They made lots of investments to improve the performance of horses and drivers. And how do you do that? Better food, shorter distances. So at the last part of the so-called S-curve, they are trying to improve, but the new technology is just overtaking. So here is a nice anecdote. Herbert Simon was quoted before. You can Google that, a comparison of the steam engine and the computer. How many have read that? Okay, so you have, it's very short, it's easy to read. So a couple of points made on technological revolutions. So they take time, usually longer time than you think, and you can relate back to the hype cycle if you remember. There is a hype, but they usually take time, and so far they have been taking quite some time. Probably, and with IT, things are moving faster, but for the physical world, things do take time. And there is no single technology. Even in the steam engine, there were multiple technologies. They needed to improve the materials. They needed to create high pressure steam and so on. They needed to control it. Multiple developments, and that's very clear today. And the good news, because it takes time, we shape technological revolutions. You're part of it. There is still time to affect it. So they take time, and humans tend to, and the hype cycle is an example of that, we tend to overestimate, we tend to fall into the hype pitfall. So we think that, okay, generalized AI, shit, tomorrow. And that's an overestimating in the short term and usually underestimation in the long term. These things will have a much more... We had the example, I think a very nice example by you and Denny, talking about, well, automated driving, that's cool, but we already have cars on the road. Wait until we have 100,000 of drones flying downtown Stockholm. That's a paradigm shift. And one example of this, of the hype and the over and underestimation, you have probably seen this, the AI winters. So AI was coined here, and the researchers, they overpromised, they oversold, and they couldn't deliver, funding ceased. And then there was the era of expert systems. There was a kind of overselling again. But now AI is delivering, and people are looking for the next step. Okay, so I'm about to wrap up. I have this view, which I found useful when I developed it. I hope you will also find it useful. So the idea is to look at innovation in CPS. So we have, you can think of technology push here, new developments, enabling things. And then we have pull here. We have demands. We want to reduce fatalities and energy consumption and so on. And then we have like a valley here with opportunities and challenges where we want to develop systems. And of course, we need a means to manage increasing complexity. We need the scientific methods, the engineering techniques. We heard Pernilla talk about complex organizations. Competencies and management are extremely important here. And typically with a technical shift, it's not just that you have new technology and new competencies and new management. You also reorganize the companies. And then we need to think at the societal level, what types of systems do we want? How many fatalities for modern automated cars? And the overall societal aspects of this, which would, for example, include, so what does democracy look like in the next century? What kind of educational systems, lifelong learning? Universities were developed a long time ago. It's an old concept. Perhaps one should never leave university tomorrow. I mean, never lose connection with university. Continuously come back. Maybe one should have shorter education and then come back. Okay, so to wrap up, course evaluation would be much appreciated. You could just dump it there. Follow-up course next year, tentatively same week, but on the west coast instead of Sweden. We have this competence network here at KTH. Some of you know about it. We have events and conferences, and you can register for newsletter and you will get informed. It's not too frequent, the newsletters. One event in particular, since a couple of years we are co-organizing this Scandinavian Conference on Systems and Software Safety with and ingredients of cybersecurity as well. It's predominantly an informal conference, say 60% from academia, 60% from industry, all domains, and 40% from academia. You have SafeComp, which is the academic side, and this is the industrial side. So it's a very nice opportunity to informally interact, in particular with industry. Thank you very much for attending.